Good morning, students. We have been discussing about stability of cycloalkanes. In the last classes, we have understood something about Bayes strain theory, Colson and Moffatt model. Today, we will understand something about the next two theories, that is Sachse theory and molecular orbital theory. Sachse theory. Sachse theory has been proposed by the two researchers called as Sachse and Mohr in the year 1918. This particular Sachse theory is also called as theory of strainless rings. The main drawback associated with Bayes strain theory is it failed to explain the stability of higher cycloalkanes. If we observe in the structure of higher cycloalkanes, it is observed that they are having negative angular strain. In spite of negative angular strain, it is reported that higher cycloalkanes like cyclohexane are highly stable in nature. So this is the important drawback or the demerit associated with Bayes strain theory, and this particular drawback could be successfully explained by the help of this particular theory called as Sachse theory. Sachse theory is also called as theory of strainless rings. Why it is called as also called as theory of strainless rings? Let's try to understand now. If you see in the structures of lower cycloalkanes like cyclopropane and cyclobutane, which are having a bond angle of 60 degrees and 90 degrees, they are all the carbon atoms of this particular cycloalkane ring are forced into a single plane. And because of this, why they are forced into a single plane? In order to have planar geometry. Because they are forced into a single plane, they are deviating from the normal tetrahedral angle from 109 degrees to 60 degrees. So because of this, they are subjected to a type of strain called as angle strain, and this particular strain, angle strain, is responsible for its instability. Right, this is all we have already discussed in our previous classes. So let's now try to try to take up understand the stability of higher cycloalkanes by understanding this Sachse theory. So the basic assumption given by Sachse is that rings can be made or rings can become free. Which free? Strain free, if at all the ring carbon atoms are not forced into one plane. See, in all cyclopropane and cyclobutane, all the carbon atoms are forcefully made to attain a planar geometry. If at all your ring carbon atoms are not made to attain not forced to attain a single plane to have a planar geometry, then such molecules will be devoid of strain, and if at all they are devoid of strain, such molecules will be highly stable. Now the next question that arises in our mind is how the molecules can be how the molecules can be made strain free, and how the ring carbon atoms are not forced into one plane. This is possible if at all the molecules, the higher cycloalkanes, attain a structure called as folded structures or puckered structures. If at all your molecules are made to attain type of structures called as folded structures or puckered structures, they can retain their normal tetrahedral bond angle, and even though their bond they are not forced into one plane, they will not have any phenomena called as angle strain, because they are attaining a type of structures called as puckered structures, and because they are having puckered structure, they retain their normal tetrahedral bond angle of 109 degrees, by which they are turning stable. So in this way, all your higher cycloalkanes, instead of having a planar geometry, they are attaining non-planar geometry. By attaining non-planar geometry, they are attaining a type of structures called as puckered structures, and because they are getting converted to puckered structures, they are able to retain their normal tetrahedral bond angle, and they are not having any phenomena called as angular strain, and they are highly stable. So this drawback associated with Bayes strain theory is successfully overruled by means of this Sachse theory. And now, how our cyclohexane, which is supposed to have this particular structure, is getting converted to folded or puckered structures? So these are the two folded or the puckered structures of our cyclohexane. This one is a chair, and this one is a boat conformation. So 6 carbon atoms, 1, 2, 3, 4, 5, 6. The 6 carbon atoms of it have been aligned in the form of a chair. So this is the chair conformation of cyclohexane, and here the 6 carbon atoms, 1, 2, 3, 4, 5, 6. They are forced into boat conformation. So hence it is said to be boat structure. So these are the two chair and boat conformations of cyclohexane which are interconvertible to each other. And if you see here, because the molecules have been folded, all the carbon atoms are having non-planar geometry, but they are retaining the normal tetrahedral bond angle. And because they are retaining the normal tetrahedral bond angle, they are highly stable when compared with your lower cycloalkanes like your cyclopropane and cyclobutane. Okay, so this is the chair conformation and this is the boat conformation. See, representation of chair conformation. First you have to draw the straight line and project it up, down, and again draw a line parallel to the above line, and again pull the line downwards, and whatever this line is there, you join it here. So in this way you can represent chair. And boat, just a normal U, extend it, join it. So this is how you can represent the boat conformation. And if we see here, each carbon will be holding 2 hydrogens, right? So 6 carbons, so 6 into 2, 12 hydrogens will be there. So it is observed that the 12 hydrogens are aligned in this way in your chair and boat form of cyclohexane. So each carbon is holding 2 hydrogens. So one is above the plane and one is below the plane. One above, one below, one above, one below. So in this way I have represented all the 12 hydrogens of chair form of cyclohexane and boat form of the cyclohexane. It is observed that out of the 12 hydrogens of your chair form or the 12 hydrogens of boat form, 6 hydrogens are equivalent to each other, which are named as axial hydrogens, and 6 hydrogens are equivalent to each other, which are said to be equatorial hydrogens. So I can say that in your chair, either in your chair or boat form of cyclohexane, 2 different types of hydrogens. The first type of hydrogens are said to be axial hydrogens, and the second type of hydrogens are said to be equatorial hydrogens, right? So what are axial hydrogens? The hydrogens which are projecting perpendicular to the plane of the ring, which are moving above the plane, which are moving perpendicular to the plane of ring, are said to be axial hydrogens, and they are represented as HA. So all these hydrogens are HA. One, two, three, 4, 5 and 6. So these 6 hydrogens are said to be axial hydrogens, and the remaining hydrogens which are moving parallel to the plane of the ring are said to be equatorial hydrogens. So these are the 6 equatorial hydrogens. So axial hydrogens are represented as H subscript A, and equatorial hydrogens are represented as H subscript E. Here also in boat form also, the ones which are moving perpendicular to the plane of the ring are represented as HA, and the one which are moving parallel to the plane of the ring are represented as HE. So in this way 6 equatorial hydrogens and 6 axial hydrogens are present in the structure of chair or boat form of your cyclohexane. The ones which are moving above the plane, which are perpendicular to the plane of ring, are called as axial hydrogens. The one which are moving parallel to the plane, which are moving below the plane, are said to be equatorial hydrogens, right? And the next thing is stability. So out of these two forms, chair and boat form of your cyclohexane, it is observed that chair form is more stable when you compare with the boat form. Why? Because in your chair form all hydrogen atoms are present distant to each other, whereas in your boat form, so this hydrogen, this equatorial hydrogen and this equatorial hydrogen will come close to each other, by which steric repulsions will develop, and because of this steric repulsion the boat structure is less stable when you compare with chair form, right? This is important for your competitive exams. Which out of these two forms of the cyclohexane, which one is more stable? Chair form. Why chair form is more stable? Because all hydrogens are distantly placed in case of your chair form of cyclohexane, whereas in case of boat form, the two equatorial hydrogens come close to each other, by which steric repulsions, these steric repulsions are called as flagpole interactions, and because of the presence of flagpole interactions, these molecules will turn, the boat form of cyclohexane will turn less stable. Hence chair form is more predominant or more stable when you compare with the boat form of cyclohexane. This is all about our Sachse-Mohr theory. right? Because the molecules are retaining puckered structures by which they are retaining the normal tetrahedral angle, and they are retaining non-planar geometry, and they are devoid of angle strain. Hence this theory is said to be also called as theory of strainless rings. Okay guys.